Okay. Does your assignment have a blank half page on the back, your lesson? Okay, watch. If you want to write this down afterwards, you can. My own diagram, which means it's going to suck. You're going to have to use your imagination, but it's a diagram that I want to be able to move around. Here's what I'm going to present to you. Over on the right, I'm going to give you a solenoid. But instead of hooking it up to a current, we're going to hook it up to a resistor, and we are going to induce the current in that solenoid. How? Over here, I'm going to have a bar magnet where this end is north and this end is south. Now, right now, nothing will happen. Right now, nothing will happen. No current will be in. This is what took scientists so long to figure out. Faraday was the one who realized, hey, you want to induce a current? Change the flux. How? Now, right now, there are magnetic field lines going off like that. One way to change the flux would be to move the magnet to the right or to the left, and I'm going to move it to the right. As I move it to the right, can you see more lines will end up going through the solenoid? That's a changing flux. We will induce a current. I'm going to erase those lines. Don't write this down yet, Dylan. Okay? Instead, I'm going to draw an arrow saying the movement is that way. We're going to induce a current. The question that we're going to ask is, what direction will the current flow in the wires of this solenoid? What direction? Well, there's two possibilities. Possibility number one is the current could curl over the top. Possibility number two is the current could curl towards the bottom. Okay? Let's look at the possibility that it curls towards the bottom. Now, this is incorrect, and I'm going to tell you why. Supposing the current went this way. Can all of you use your right-hand rule on the solenoid? Can you tell me which end of this solenoid would be north? Which end would be south? What would this south pole do to that north pole? Attract it, which would mean what would happen to this speed? Speed up, which would mean what would happen to the change in flux? Get bigger, which would mean what would happen to the current? Get bigger, which would mean what would happen to the south pole? Get bigger, which would mean what would happen to the force of attraction? Get larger, which would mean what would happen to the velocity? You know what? That's perpetual motion, that's free energy, and the universe comes in and says, no. 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 The universe, as soon as I start to create a magnetic, and create a current, as soon as I start to try and induce this current, erase this, by moving a north pole closer, the universe is going to say, how can I oppose that? What would oppose a north pole moving closer? The universe is going to come in. It's going to put a north pole right there. It's going to decide the direction of the current, and the way it's going to decide the direction of the current is, I kid you not, I'm kind of personifying the universe, but it says, how can I make it so you don't get free energy? I'm going to resist what you're doing. Which means that now that I know which way the magnetic field has to be, otherwise I get free energy, I can point my thumb, our right thumb to the left, and now I can tell you what direction the current flows. The direction the current flows, and now I can follow it through. You know what? It goes through that resistor from left to right, not from right to left. That's Lenz's law. It's an English law. And it's a rule in English, and it says, hey, you want to know which way the current is going to go? Ask yourself, what's the change in flux causing the current? The universe will create a change in flux in the opposite direction. Okay. I will bring this diagram back later if you want to copy it down later, if you still feel like you're a little bit, but I always start out the lesson with this one because I can use color. So let's go to the lesson on the front page and then remind me to bring that diagram up at the end. So here's Lenz's law. It says, consider the following situation. Will there be an induced current in the coil if we move that magnet to the right? Well, the answer is yes, since the change in flux is not zero, since there is a change in flux. What direction? Moving a north pole closer, what would oppose a north pole moving closer? A north pole right there, a south pole right there. Okay? Oh, which means now I can point my thumb to the left, and it looks like the current, if I use my right-hand solenoid rule, would be flowing that way. By the way, going back to this diagram, what if instead of moving the magnet to the right, what if I moved the magnet to the left so that I had a north pole moving away? What would oppose a north pole moving away? It would put a south pole right there. The current would flip. This is why we get alternating current from our power generation. Because it's way easier, it's just much easier to flip the current. Question? Say, I missed that. I heard eventually the end.
It would push the magnet left, and then it would switch.
It would push the magnet left?
Yeah. When they get to a point where it slows down to zero, then
We're having some kind of external force pulling the magnet, like a human being, or think gravity in a water turbine. I think I've understood your question. I'm not sure I did. Let's keep going, and I'll come back to it, because I think it'll become clear. This is Lenz's law. You need to know it. It's not an equation. It's not on your formula sheet. It's given in English. Like I said, Faraday liked English rules. An induced current will always create a magnetic field that opposes the change in flux that created the induced current in the first place. In other words, you get nothing for free, ever, except maybe your mother's love. Maybe. This also explains the negative in Faraday's law. This negative right here tells us that the induced EMF, that induced voltage, is created by a current that's creating a magnetic field opposing the magnetic field that created the current in the first place. Let me give you some examples. Here are some classic questions I'd love to throw at you. Example 1. A loop is placed in a region of magnetic field that is into of the page. I guess I need to delete the word of. Into the page. The field then changes direction so that it's now pointing out of the page. That must mean there must have been a change in flux, because at one point lines were going down, now lines are going up. You've changed the flux by changing the direction of the magnetic field. What direction will the induced current in that loop of wire be? Now here's how you answer this. Look at the final magnetic field. What direction is the final magnetic field? Out of the page, nature will create a magnetic field opposing that. What's the opposite of a magnetic field out of the page? The magnetic field created by the coil will be into the page. So all of you point your thumbs into the page and tell me what direction the current will be flowing in that coil. Akemi, clockwise or counterclockwise? Let's add arrows. Clockwise. That's how we'll give you the pictures from a looking down the coil end on view, as opposed to the first one that I drew with you, which was a side on view. Okay. Example 2. This diagram shows an aluminum ring and the current induced in it by the nearby magnet. Now that magnet is free to move left or right. We don't know which way it's moving, but what they have done is they've told us which way the current is, the induced current. So I think if I look at which way the induced current is creating a magnetic field, and I remember that it's in opposition to whatever we're trying to do with that bar magnet, I think I can reason my way there. So if I curl my fingers in the direction of the induced current in the coil, the induced current is creating a north pole there and a south pole there, yes? That is being created in direct opposition to whatever you're doing with this magnet. So how could you move this magnet here? How could you move this bar magnet in such a way that would cause nature to want to put a north pole there? Specifically, look at this south pole. Huh? It's moving to the right, because what would oppose a south pole moving to the right? A north pole right there tugging it back. See the reasoning? Patience, young grasshopper. Okay? Example 3, now we're doing our looking down the coil, except this time I've attached the coil to a resistor in a circuit. Will the induced current below flow from X to Y through the resistor or from Y to X? Again, look at the final magnetic field. What direction is the final magnetic field? Nature is going to resist that. What's the opposite of out of the page? The universe is going to create a magnetic field in that coil into the page. Point your fingers into the page, please. Which way will the current flow through the coil? Clockwise or counterclockwise? So add arrows and now follow it through the circuit. From Y to X, yes? Example 6. If we're moving that magnet to the left, find the coil's induced north pole and the direction of the induced current. Okay. Always look at, if it's the side-on view, look at the pole that's closest to the coil. I don't care about that south pole, I'm looking at that north pole. How is that north pole moving? Towards or away? What would resist a north pole moving away? Figure it out. Try it on your own, I'll do it up here. Okay. I wrote down here, Mr. Dueck will now show you a demonstration that's as close to magic as you'll ever see, unless you know about Lenz's law. So we're going to use our imagination. We're going to say, suppose you had a long metal tube. You can, or you can watch. And in that metal tube, you have a magnet in free fall. Let's put the south pole there and the north pole there, and it's falling down. Right here, you have a north pole moving down. You can treat this piece of metal, this metal tube, whoops, you can treat this metal tube basically as one huge solenoid. A bunch of wires wrapped together, okay? So we are going to induce a current. What will we induce underneath the magnet? Well, what would resist a north pole moving down? Okay, a south pole pointing, a north pole pointing up? Is that what you're saying? So right here, we're going to induce a current in that direction. That's going to give us a north pole there and a south pole there. Oh, above the magnet, right here, I have a south pole moving down. What would resist a south pole moving down? Right here, we're going to create an induced north pole and south pole. Right here, the current is going to be going this way. That way. You don't get a net current because can you see the top above and below are opposite directions? But you do get magnetic fields, and this magnet will not fall the way you think it does. So there's Lenz's law. You'll notice I don't think I gave you any actual homework. Well, the reason is these don't require diagrams. Your homework is actually going to be from the big ultimate magnetic induction review. So stay on this piece of paper here. Just write down these questions. These are the ones you can do from the review that involve Lenz's law. There's a few of them on here, Mr. Dueck. Show me a direction question. Number 9. Nope. 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 Good gosh, is there only one? No, it's got to be more than that. I know there was more than that, Mr. Dueck. Number 22. 22 is actually looking at the same situation that I just showed you with a copper rod. 25. Uh, 27. 27, they're also wanting you to find the magnitude of the current. I think you're going to use V equals I times R, except instead of V, you're going to use EMF, which is negative N, change in flux over change in time. Ooh, nice combination of everything here. No, that's cool, though. Come on, Lenz's law. Here, Lenz's law. I don't think you are. But I'm suddenly going, maybe I only have a few examples. Good gosh, I only have a couple of examples. Okay.